Hello everyone and welcome to Handmade Hero, the show where we code a complete game live on stream. We are in the middle here of doing a conversion of our OpenGL fixed function pipeline code to sort of the more modern core OpenGL pipeline now that we have everything working. And yesterday, we stopped right at the point where we had sort of moved over to, we sort of began the move over to more of a streaming triangle system from something that was more logical based. And today we're just going to try and finish up that move, or at least the first part of that move, which is what will put us in a good position to do sort of a cleaner and more modern OpenGL pipeline. So that's all we're doing right now. If you followed yesterday, then you kind of know what we're doing, because we stopped at a point where we were like, all right, here's this working with just one batch, and now we're going to try to make it so that it sort of buffers up a large number of triangles rather than just one a single quad per batch. So that's all we're really doing here. So let's go ahead and dive in. Today is day 371. So if you want to follow along at home, you want to start with day 370 source code. Let's go ahead and open up the project. All right. Alrighty, so if I go ahead and run it, you can see that we've got everything working relatively correctly here. However, as you know, each of these sort of sprites that you see on the screen is drawn with a separate, in our render is putting a separate entry in for each one of those. But the whole point of what we did yesterday was to make it so that we no longer have to do that, at least on the submission side. So what we did is we added this thing here called render entry textured quads. Those textured quads is just a number which says how many quads are going to be, and then an offset into a giant buffer full of vertices where the vertices for the quads get pushed. Alongside that is a parallel array of bitmap pointers. Each bitmap pointer corresponds to one of the quads. So for every quad, we can say, here's the bitmap that we want to draw with that quad. Right? So that's all we want to do here. And if we bounce back over to the OpenGL code, we can see that actually we're ready to support that quad count being anything it wants to be. It loops over the quad count and just draws whatever it finds there. It's still submitting it via the OpenGL fixed function pipeline. So like I said, well, not quite. I mean, it's switching to its own program, but the vertex submission is via the OpenGL fixed function pipeline. What we want to do is switch this over to be a more modern version that doesn't use the fixed function pipeline, which or at least I should say, we don't want to use immediate mode submission. So that we'll be a little bit more modern. Immediate mode submission is kind of old at this point. So in order to get to that point, though, what I want to do first is just make it so that rather than sending these down one at a time, and because all of our entries right now have a quad count of 1, and so it's just one quad per. What I want to do is get to the point where we're sending down a large batch of them at the same time, right? So many quads. Like I said, we'll still have a problem with the bitmap part of things. And we'll talk about that a little bit later. But for right now, we're just trying to get all of our vertices into a more sane submission way. My nose is very runny, so you're going to hear a lot of nose blowing on today's stream. It's not going to be pretty. I'm not sick. It's just allergy season. The weather's getting warmer, and it's always rough when the weather gets warmer in Seattle. All right, so here we go. What we want to do is essentially take all of these calls inside our handmade render group. And right now what we're doing is every time we push a bitmap on, you can see this is the call for pushing a bitmap here. Every time we push a bitmap on, you can see us doing this process where we actually create a new entry, render entry textured quads, every time. Right? And so what we want to do instead is just, if we already have a render entry textured quads lying around, then we will just add to it, right? That's all we really want to do. So what we want to do here is basically say something like, okay, inside the render group itself, what I want to do is say at the end, and you can see I stuck it here, at the end of the thing, I'm just going to have a notion of the last render entry textured quads we pushed on there. And every time we get a new one, what I want to do is just append it, right? I just want to append the new data to the old textured quad struct, okay? So what I want to do when we come in here to push bitmap is say, all right, there's an entry for this thing, right? And the entry is going to be the current quads. Oops. Right. So the entry is going to be the current quads for whatever this render group is. And as I go with this current quads here, I'll know when I look at it if it's not there, right? If it was set to 0, so current quads doesn't currently have anything in it, then I'll push a new one. Right? And I'm not going to use this plus size of loaded bitmap here. We'll see why in a second. So I'm just going to push the new render entry textured quads struct on if I don't have one. Right? That's what I'm going to do here. And then assuming that I got it, now if there's an error case and we ran out of memory, then this will fail, this if will fail. But assuming that I got it, then also what I'll do is I'm going to save it, right? So in some sense I could also do it this way, I suppose. This might be a little better. Right? So basically if that, if that member isn't set to something, let's fill it in. Okay? Then we grab it out and we go from there. And then for that point, the only way this would be 0 is if we ran out of memory for our stuff. Right? Okay. So the other thing we can do here is move our assertion up to make this more robust as well. We could say, all right, the other thing we need to probably know is that however many vertices we have so far, that if we were to push 4 of them on, we would not exceed our maximum vertex count, right? So we'll also clip that off there. And then there's one other thing we're going to have to check, and you'll see what that is in a second. So once we push this on, you can see that we could just go from here because the vertex array stream is all fine and dandy. But we end up in another sort of problem where we've got these loaded bitmaps, and the loaded bitmaps are in the same they have the same situation as the vertices, right? We're sort of pushing them on one at a time. We need a place for them to go. And so it seems like probably what we want to do here, and it's hard to say, but it seems like probably what we want to do here is just have that be also part of the stream. We could put it as part of the memory that we're using as the push buffer in this case. But I'm not sure there's any real point to doing that because we know that we've got a fixed vertex size buffer. We might as well have a buffer of pointers as well, right? And so I think what we want to do here is say, hey, just drive this off of the vertex count. Since we know the vertex count corresponds 1-to-1 with the loaded bitmaps, let's just use that, at least for now. If that changes, then we can do something different, obviously. But so all we need to do here is say, all right, let's get rid of the bitmap array concept. And instead, what we'll say is the commands bitmaps or quad bitmaps. I don't know what we'll call it. I guess we'll call it quad bitmaps. So we have our quad bitmaps, and we just want to set, like we were setting here, we just want to use whatever the vertex count basically divided by 4, right? So we're basically just shifting down by 2 the value of this thing and saying whatever that, whatever the vertex count is, we know that we want 1 bitmap for every 4 vertices, and so off we go, right? And like I said, we can play around with that a little bit more if we get fancier later, but for now, that would be all we would need. And so that will just work, except for one slight problem, which we can talk about in a second. But what we do know is that if we want that to work, we will need, in our platform layer, to supply also the buffer of pointers here. So if we come up in here and we wanted to put a loaded bitmap struct in here, we would say this is quad bitmaps, and that would have to be initialized to the same size. All right. So moving on. Oops, I forgot a pointer in there. This is pointers to bitmaps, not bitmaps themselves. So in the platform layer, that means that has to be allocated as well. So what we want to do here probably is say we've got a block that's just the max vertex count times loaded bitmap star, and then that's going to be loaded bitmap star star bitmap array. And inside our platform initializer, when we do render command struct with that vertex array there, we also want to put the bitmap array in. And so when we go ahead and specify that, we'll just push it on here. And now the platform layer sends those buffers down, and it's off to the races. Oops. So now we should have exactly what we expect to have. In fact, I can, if we want to, have this happen every time, where we just say, let's allocate one each time we go, and this should still work, right? Except for the fact that we forgot to have the reader do the same thing. So let's quickly just do that as well. So on these, let's go ahead and get rid of this bitmap array here. All right. So since we have the vertex array offset in there, again, the vertex array offset divided by 4 is all we would need to know where to load the bitmap from. So in terms of the bitmap at, all we really want to do is just say, in fact, bitmap at doesn't really need to, yeah. So all we need to do here is say, well, we're going to grab the quad bitmaps, and we're going to offset by the vertex array offset. But again, we just want to divide that by 4. So we just want to say, like, all right, use the same offset into a separate array, but just get one every 4 instead of one every time, right? And so that's all we need to do. Furthermore, we no longer need to do this offsetting here, because now we're back to just adding the size that the actual struct is. We don't have to advance anything else, right? And so here we are to where we were before. And all we have to do to finish this transition now is just make it so that when we're inside the render group, we actually push this on in some kind of coherent way. So if you take a look at what's happening here, if we have a current quad structure, when we come through here, this quad count, right, is going to be something that could be, already set, right? It might be 0 in the case of if this is the first one. Oops. So if this is the first time anyone's pushed one on, so if we hit this path, then this would be 0. But if we didn't hit this path, then it wouldn't be, right? And same is true here, where we're going to only set that vertex offset the first time, right? So those get set the first time, and then every time thereafter, when we look at the quad count, what we're really doing is just incrementing it, right? We're saying, okay, we're going to add another quad, 2 triangles, right, onto the end. And so as we go through here, you can see all the rest of this stuff should stay essentially the same, except this bit right here where we're looking at the vertex count now has to be a little bit smarter, right? It has to use the vertex array offset for the vertex count, and it needs to add the quad count times 4 to that, right? So in here we've got sort of the vertex count, which is a separate thing now. Oh, actually, you know what? No, we don't. Why am I saying that? This will still increment properly. So actually all that's, I guess, just fine. So I think this all just works as it is, and this will append to the current quads as it goes, right? So now the only question becomes, well, when do we have to stop using current quads, right? And the answer is anytime someone does a push, right? Anytime someone does a push that might affect what we are doing, then we need to, because these things get retired in order, right? Anytime someone does a push that's not one of these quads, technically if we want to preserve the order, then we have to do it. So for example, if we push a bunch of quads, then do a clear, then push a bunch of quads, we have to execute the clear in between those two if we want to preserve the order that people sent them down in. Now the things that we are setting, again, most of these will go away. So bitmap, cube, and rectangle all go away. So the only things we'll be pushing are clip recs, blend targets, and textured quads. And so obviously if we pushed, say, a new clip rect, we need to respect that clip rect as we move forward. And so, change the transform, change stuff like that actually is important when we're pushing quads. So anytime we do a push of that nature, we're going to have to clear it out, right? So what we need here is something that essentially says, all right, every time you push a render element, we need to clear the current quads. And I think that should be sufficient for now. We may have to be a little bit smarter about that later, depending on the sorts of stuff that we push at the end. But I think that is sufficient. And there you go. So now we are submitting everything as part of this, these sort of quad batches. We can take a quick breakpoint into the OpenGL layer to see how big those quad batches end up being, which is kind of just something to be aware of for our own sort of sanity check here. So let's take a look at how big the quad count is when we go through a couple different cases here. So not great, and I'm assuming that part of the reason for this, let's see if this is true, is do we push, I don't know what we do inside the entities, do we push a transform every time on the entities? Yeah, we do. Wait, or do we? I'm going to set a breakpoint inside push render element. It might just be because we push cubes and other and entities interchangeably, and when we move to cubes, it'll be fine. But let me just double check here, because again, I want to make sure we don't have any funny business going on there. All right, so here we are in push render element. This is pushing a setup, so we don't care about that one. Here we are drawing hit points. That draws a rectangle, rectangle, rectangle. Drawing a bunch of rectangles. Okay, there's a push bitmap, there's a push cube. So you can see they're kind of sandwiched in there. Why is this feeling so sluggish? There we go. I can actually see what's going on. So a lot of these are push cube calls. So maybe the best thing to do would just be to switch, do a push to the push cube. All right. So let's take a look at something here. Let me just go ahead and really quickly move the push cube in there too, because there's no reason we can't do the push cube in there as well. Because right now, we can't aggregate much because push cube gets called a lot. All right, so if we come up through here and take a look at render group entry, render type entry cube, let's just grab that out and make that work in the other way. Now, we do a disable of GL texture 2D here. And so I'll replicate that behavior temporarily just because we don't have any textures to slap on here. But eventually that would go away, right? So in here, where we do the bind texture call, right, what I'll do is I'll just do if bitmap else. And I don't know, so here's a question. I'm not really sure what will happen. If I bind no texture, let me just see what happens if I don't bind a texture. I'm curious if we draw white or if it's all black. It's all black. So I do have to disable. What I could do is make a texture that's the untextured texture, which is probably the better thing to do. But like I said, temporarily, since this is not really a case that I care about, I'm probably not going to bother. All right. So in here, let's just go ahead and say that in this case, we do a disable. Okay, so we do a disable if we have to for 0, and then we come and we re-enable it again at the end, like so. And that will allow us to just do the cubes the way we are doing them now as well, just for debugging purposes. So when someone does push a cube on, again, all I'm going to do here is I'm just going to grab the render entry cube code exactly as it is, and I'm pretty much just going to translate it into something that pushes the vertices on as they are. And rather than pushing just that description of the cube, it'll just push the vertices on, and off we will go. And so we could do the exact same thing for the rectangles too, but one thing at a time. So let's get rid of render entry cube here, and in fact, I'll actually just get rid of render entry cube in its entirety. And now I just need to actually convert this stuff. So instead of pushing render entry cube, instead what we're going to do here is I'm going to do the same thing that we did for getting the render entry quads. So what I want here is I want a little utility function that'll just do essentially this right here. So this code we'll basically get the current quads out, like so. And when you call, let me just put that into a, there we go. When I call this function, it'll check to make sure that we actually have some. If we don't have some, it'll make some, and then give it back. So then whenever we do this, I can just say get current quads and pass the group. And then anyone who wants to do this can just take a look, right? The other thing I can do is make this be more of a sort of automated function here. So what I can do is in here check the if to see whether or not the thing that's going to be put in there will fit. And if the thing that's going to be put in there won't fit, we'll pretend that we didn't get one, right? So basically in here we'll say what's the number of quads that you intend to push, like so. And then what we can do is say, well, all right, if the current vertex times the quad count, plus the quad count times 4 is going to be greater than or equal to, or just greater than the max vertex count, then then we'd be in trouble. I guess we could also just, since we know that the amount's the same, well, no, I guess that's all we need to check, because we know that the bitmap array is also exactly in line. So we could just say that 4 times the quad count plus the max vertex count. That's really all we need to know, right? So when I call this, I know that this is only going to push 1 quad on. In fact, I guess we could also increment this. Now, let's leave that in case the other person wants to do it. All right. So there's our quad count. For push cube, we want to do the same thing. So I want to have a render entry textured quads. I want to get that entry. I don't know why I just deleted that. And so I'm going to do get current quads here, and I'm going to pass the group, and I'm also going to say how many I want to push. Obviously, I need one for quad for every face of the cube, which is going to be 6 faces total for 6 quads. And then when I come through here, I need to now place the stuff in that I need to record, right? All right. So looking at all this, most of this code can stay the same. Right, most of this code you can see here, we've just got pre-mul color on there. Otherwise, we just have bitmap p, height, and radius are actually all directly stored. So all of this stuff should work. Instead of cube p, we should just be able to use p. And instead of like cube arrow, we can use that radius and height for everything. And then these p0, 1, 2, 3, those all stay the same. All of these computations will all stay the same as well. Everything here should be roughly correct. And then we don't need any of these sorts of things, but we do need to record the bitmap texture handle in this case, right? But it's just going to be bitmap for our purposes. So we need to record this. We'll do that in 1 second. And then we need to actually make these quads into vertex pushes, right? Now, what you can see here is we sort of have a notion in GL land that it would be easier if we could just say, hey, here's here's a quad. So what I probably want to do is just say, push quad, and have a way to push the quad onto the entry directly, right? That seems pretty much like the way I would want to do this. Because that way I don't have to write code separately to push these every time. And similarly, the code for the bitmap pushing could do basically the same thing, right? There's no reason we can't just use this in both cases. Now, in terms of the top color, bot color thing, obviously at this point we want to turn these, we want to turn all of these things into 32-bit ones. We could, because we could pack these ahead of time. I'm going to not do that at the moment. I'm going to let that happen in here. But because that's an optimization we probably don't need to think about too much at this point. So here's push quad. The compiler might even just do it for us. So assuming we have a render entry textured quads, we're just going to go ahead and increment that quad count here. And then I'm going to grab this stuff where we've got the quad bitmaps. We've got the bitmap here and all the output. Here we go. So I'm just going to go ahead and make this function do the logical thing. So we need a bitmap. And we also need, we're going to need to pass the game render commands here. I guess we'll pass the render group. And in fact, we could, if we want to, just get this out of the group as well. All right. So when we push this quad, we need the group. We need the bitmap that corresponds to this quad. We will push the quad on here. I guess this is kind of a little more sane to do this way, probably, huh? We'll push the quad bitmaps. We'll push that bitmap that got specified. We'll take a vertex from the vertex array at the location we expect. We'll add 4 to it so that we know that we've recorded 4 of them. And then in here, where we've got the vertex stuff, we just need to basically allow these to be passed directly. So we just have, one for each of these, like so. Let's go ahead and clear these out. And these are just numeric, right? We're going to push one piece of data for every vertex here, and we're going to pass that data in. So here's the P0, here's the UV0, here's the C0, and we just want 4 of those. Right? So that's all we need to do the push quad. And so what we can do here is say, oh, all right, if we're going to do a push quad, we can just now wrap all this up as well. So we can say, okay, we need to pass the render group, we need to pass the bitmap, and then we need to pass each of these things. So there's the P, there's the UV, there's the color. Oops. And again, this is just making it a little easier to push these on, so the code's a little more concise, and we're not repeating ourselves over and over again. Oops. Clipped off a Y there accidentally. There we go. And so we've got our push quad working in both places now. And so these should basically both be the same. Now the only difference is we have one that is if you have pre-packed colors, which is this one. And so all I want to do is also have one if you don't have pre-packed colors, just to make it a little easier. And so all I'm going to do here is say, well, if you want one that will pack the colors for you, we can do that as well. And all that's going to be is if we just do RGBA pack 4x8, we're just going to do that pack, this call right here, basically, the 255 times the color value, right? And again, that's just to make it a little easier for anyone who wants to call it who doesn't already have them that way. There's no sense in not just having a utility for it. So there's just another push quad that'll happen, that'll automatically do that push, that'll do that conversion. So now this code should be relatively correct. The only thing we have to do is actually push the bitmap in here, because this code wasn't set up for that kind of work. And instead of the entry, this is a group, right? So inserting that in here, we end up with that. And I think that's basically it, right? We also have to come back up in here and say, well, we don't need to, oops. Excuse me. We don't need to do this anymore, because that's already taken care of inside the push quad call. And now, in theory, both of these are correct. All right. So we got to grab that commands array out here. I also don't know, does this do that anymore? No, it doesn't. So this actually doesn't need the commands array anymore. So that's strictly happening inside here and here. All right, so the Primo color for the top cube is, the top color is just this. And so we've got that down. And then push quad, okay, can't convert all the argument types. What have we got? V4, V2, V4. I thought we had that one. Do we not? Render group, loaded bitmap. V4, V2, V4, V4, V2, V4, V4, V2, V4, V4, V2, V4. That's this one. These are V3s. Well, that's certainly easy to rectify. So none of these need a z-bias on them. So these can all be set to a z-bias of 0. And then I think that's all we need. Yeah. So in theory, our cubes should now be going down, and they almost are. It's just I forgot that we had the bitmap set. So they're still getting a bitmap on them for now. We wanted to set that off. That should be turning off the texturing. Oh, All right, so that's actually not true. Now that I think about it, this is one place where we can't lean on the fixed function pipeline anymore. It's going to force us to actually not do that anymore. So once we do use program, we're not going to be able to turn off texturing. I totally forgot about that as one of the things that's definitely going to be the case. So once we do a use program here, we won't be able to disable GL Texture 2D. So pretty much this to-do is going to have to get handled immediately because we always have to bind something. The reason for that is once you switch to use program, the parts of the fixed function pipeline that would have affected that would have been about compiling the program no longer have effect. So if you take a look down here, what you can see is we do this text sample equals texture sampler frag UV call. I believe that will just always fetch from the texture. So we have to have some kind of texture bound to the sampler because the sampler will sample something. Now we can bind just a straight white texture to it if we want to, but we have to bind something. And that's just going to be the way it is. So, yeah. We'll have to make a pure white texture or something like this. For now, it's OK. We can just leave it like this. I don't mind, because we got to switch to having some something else in there anyway. But as you can see now, all of our stuff is going through that pipeline as evidenced by the bug we just had, which is great. Right, that's what we wanted. And so now that more stuff is going through there, let's just get rid of the vestigial remains here. Well, actually, you know what? Let's do one more first. Let's go ahead and put push rect in there, and I guess that'll force us to do sort of the white texture thing that we were just talking about. So trying to think about what the most efficient way is for us to do this. What we'd really like to do is have had a sort of a pure white bitmap that gets created as a texture that sort of just sits around, and then still have a bitmap handle we can use to talk about that, right? And so I'm not sure what the best way to do that would be, but it probably looks a little bit like probably looks a little bit like, okay, like that. So if we just have a loaded bitmap pointer that's basically just like the pure white texture, we could do it like that. It might be better to have the asset system do it. I'm just not sure. I have to go back and see exactly how we would do that, because the asset system, I don't know to what extent it really has support for doing something like that, like solid color bitmaps. Now we could add it. I just don't know if it's worth adding it, because I'm not sure if there's really much point to it. When we do the load asset work directly stuff here, you can see we have a finalized bitmap call. I mean, really what we want is just for our asset pack to have one of these in there, so you actually just ask for it. And the other thing is, I feel like if we put it through the asset system, it can get paged out, right? I mean, like technically. So it's not really that kind of asset. It's kind of something that just wants to be resident permanently. And so I kind of feel like it's something that wants a special path. That's just how that's my gut feeling about it, you know? So yeah, I don't know. I think that should probably look this way. Something like this. And so then whenever we're doing something like, for example, if we are doing the cubes, there we go. So we have a thing here that's like get bitmap, and we pass down the ID. I guess mostly what we want to do there is if that bitmap ID was like the, that bitmap ID, we want it to be able to return that white bitmap. Let me take a look. Yeah, I don't know. It's a tough call. I feel like that's the best way to do it. Let's just take a look at what that would look like inside the Win32 side of things. So if I'm in here and I've got this initialization code going on, at this point, OpenGL has been initialized, right? It's going on right here. And we've gotten back an OpenGL-RC. So I think, what I probably want here is just to say like, okay, we've also got a loaded bitmap that's like white bitmap, right? And when we're setting up that white bitmap, we need to say like, okay, that white bitmap is going to come from the OpenGL layer. So it would be like, it has to come, I guess, from whichever layer. It has to come from whichever layer is doing the current rendering. Now, I guess that's not technically true because it can be both. It can actually just be a white bitmap that's actually in memory as well, but it just has to be one that corresponds to. Yeah, so I guess it's fine. So what we would basically say is, okay, OpenGL white bitmap or something like this. And I guess we don't even need to do that. We could just do it when we do the render commands. Like so. And so then what we'd say is, okay, inside the OpenGL layer, when we initialize, we know that inside OpenGL we're going to have a GL uint that's the white bitmap ID. Well, actually, I guess we'll just have a loaded bitmap. That's the white bitmap, like so. And on initialization, in here, what we do is we'd make one of those textures for the white bitmap. So inside, we've got, where is that? OpenGL allocate texture, like so. We would have that in here. Oops. And our loaded bitmap, in this case, would need a place to store its pixel, which can be right there. And I think this would actually technically need to be aligned, though, for the software renderer. I don't know if we actually... No, it doesn't, because they're texture fetches, so that's not true. So when we do an OpenGL allocate texture, in this case, we're just going to do a 1 and a 1. And the data is going to be that white value. The OpenGL white bitmap. We now need in our bitmap. We now need to fill these out. So the white bitmap memory equals this. The align percentage, let's just say it's centered. Why not? The width over height is 1 because it's the same, it's square. The width is 1, the height is 1, the pitch is 4, and the texture handle, I assume OpenGL texture will return this to us, but I don't remember. That is true. And it looks like loaded bitmap isn't defined yet when we are here, which should not really be the case. Where was that defined? It's in a render group. So I'm going to go ahead and move that to render. Because it should have those, right? Why does it not have, when is this actually included? Because OpenGL.h should have a bunch of that stuff. Let me take a look here. So in Win32 Handmade, yeah, so render.h is included. It's not included before this, I guess, so it needs to be up here. There we go. I can't see, but I'm sure I know what to do. There we go. So I think that's mostly it. Now all we need to do is inside the platform layer, we need to make sure that we're actually going to have a way to push that on there. So this is the white bitmap, like so. And now what we do is inside Handmade render group, what we need to do is make a version of PushCube that takes the pointer directly. So this is just a case of having a double call like we have in the other case, where if you pass a bitmap ID, it'll do the get bitmap for you and call PushCube redundantly, like so, or rather as a thunk. With the actual bitmap. So that way you can call either one, and it allows you to pass the white bitmap directly if that's what you're trying to do. So similarly, push bitmap in either case here. Again, we'll do the exact same thing, and I think that's all good. There we are. And my head is in the way. There we go. So this should just work. Now, if we want to start using that, I really have to update my keyboard bindings to the same ones as at work, so I don't keep trying to hit 6 to indent. So now all we have to do if we want to change something to a white bitmap is when we actually call whatever that something is. So for example, in this case, what we can do in this now is if we want to get the white bitmap, we can just say, you know what, use the white bitmap from the render group, and that should be a solid color, and at least in theory. So, guess the only thing left, the reason that we don't see anything at this point, is we haven't actually initialized that to anything. So the OpenGL white color just needs to be basically all ones, so it's just 255, 255, 255, 255, and then it should be a texture we can bind that's just solid. Oh, my goodness. That's not what I expected at all. I'm not sure how we managed that one. Does it think this texture is bigger than it actually is, or did we set the border type to not be clamp or something? That's fascinating. You have to admit that was pretty cool. Now, one thing we probably will have to do is that white texture, if it's ever used, is going to have some padding because our software renderer, I think, had some padding requirements as well. But that's sort of here. So we've got clamp on the S&T. I am really not sure what the deal is with that. And there's no sRGB involved here because everything is 255s. So it's, you know, that is pretty fancy. I don't know what to make of that. So it looks like for whatever reason we're getting a lot of alpha in there, but I don't know why. That's a puzzler. We have a white bitmap with a texture handle we allocated from OpenGL. We're sending it down just a basic white pixel, a single white pixel. I'm pretty sure the submission format is just RGB, right? Like, here's the allocate texture. We're going to get a texture. We're going to bind the texture. We're going to send it down. It's BGRA. It's a width and height of 1. It's got a linear minification and magnification filter, but no bitmaps have been specified, so it wouldn't matter anyway, presumably. And it's supposed to clamp at the border. Let's see what happens when we step in there, I guess. Maybe there's something weird going on that's not what I would assume. That's definitely the value we would expect. We generate a handle. It's handle 2. We're going to send down the texture here. It's unsigned bytes, width of 1, height of 1. Specify the texture parameters. Stop binding it. Put the handle back in. And that's all there is. Ah. Well, while I can't say why that would be a problem in this case, that's definitely a bug that I'll fix. So since we're using this as something that sticks around now, OpenGL init would have to basically be a destination-based thing, like so. Oh wait, no it doesn't. What am I talking about? OpenGL isn't, that's just the info structure. I don't know why we're returning the info structure either when it's getting passed in here. In fact, why are we doing that? Let's get rid of that. There we go. That's a global. So since OpenGL is a global, what I was thinking would be a problem was definitely not a problem. So I saw that return thing there, and it's like, oh, we're returning by value. But we're not actually doing that. So this should be fine. So I don't know what's going on there. I'm curious now. I wonder what happens if we just make this be something else. Just so I can see what's going on. Do we have a set call? No. So I just want to see what happens if I actually give this bitmap some size. I thought it might help me understand what OpenGL is drawing. Let's take a look here. So it looks like maybe let's be a little bit more aggressive here with our test art. So it looks like it is definitely using the color value, but it looks like maybe it's the vertices of the cube that are broken and not our texture. Is I guess what I would say there. So let's see if that's true. Let's go ahead over to render group and see what the problem is there. So is there some reason that the vertices of the cube would be broken compared to, say, our bitmaps? So we are using a different call. We're using the RGBA pack 4x8 call, right? Whereas the other one is doing the pack and then calling. Meaning the push bitmap, which is, as far as we know, working properly, isn't using that path. So, but I don't think that should have much to do with it. I mean, in this case, let's step in and find out, I guess. So here's our two colors. We've got one that's sort of got the green in it, and one that's got nothing, right? But they both have an alpha value of 1. So, you know, we would expect no alpha here. So let's go ahead and step in to push quad and see what we end up with. All right. So all of the alpha values for these colors are all full alpha, right? So I would expect to see, let's see what the UVs are as well. So I would have expected to see no alpha, right? Because the alpha value is 1, exactly like I would have expected it to be. So yeah, I'm still really not sure what I'm looking at there. It seems like a vertex problem, but at the same time, I'm not sure how it could be a vertex problem if it doesn't look like that when we switch to a different texture, right? So for example, if I go back to entity and switch it, like so, this doesn't look that way, right? This texture looks correct. So it really does look like something texture related. Because only when we set it to the other texture are we having that problem. That's a real puzzler. I don't think I have a good idea about what would be happening there. I really don't. We are using multi-sample, and we do have alpha to coverage on. So that explains the banding, because obviously the coverage values make it so that because that cube is setting its alpha value, the alpha is going into the coverage, and the coverage therefore is saying, hey, you know, you've only got 8 steps of brightness here, right? You can kind of see those 1, 2, 3, 4, 5. Kind of gets a little hazy in there. 6, 7, 8. So you can kind of see that the alpha to coverage is doing that, but I just really don't have any idea why I would be getting that pattern when I should be sending down full alpha everywhere. I don't know where the alpha, how the alpha is getting set to something yeah, to something else. So let's try a couple other things here just to provoke. Sometimes you just got to provoke. When we allocate this texture, you know, normally when we do allocate texture, we get the linear filtering. If we were to turn linear filtering off, so just temporarily, I'm going to add a thing here that just does nearest. So no filtering. You're just going to take whatever sample you think is closest. So it's only the filter that's grabbing black somehow, or at least something with an alpha value of 0. It's almost like it's disobeying our GL clamp call. You know what I'm saying? It's almost like it thinks there's a texture border. And it's fetching into the texture border. I'm just curious, so if wrap S and T are set to GL clamp, let's just take a look at what those are now. Maybe I need to set something slightly different. Do I need to set clamp to edge instead? Let's just try clamp to edge. I didn't think there was a difference between those two things. I didn't even know there was such a thing. I thought clamp was clamp to edge. Maybe it's not. It's phi clamp to edge. Huh. So what is the difference between clamp to edge and clamp? Somebody tell me. Obviously, I don't know the difference between these two things. So for those of you who don't know, texture wrap is basically just the way in which texture coordinates are processed if they're outside the 0 to 1 range. So obviously, as you would expect, if you have something like GL repeat on, you can go 0 to 1. Then when you go from 1 to 2, it'll repeat the range of 0 to 1. So just like repeat, it'll tile the texture, right? Clamp is supposed to just clamp it to the value that it gets to at the edge, but I guess that's not exactly what it does. I would like a list of these somewhere. Let's take a look at the OpenGL latest spec and just see what it says in terms of GL clamp, because I guess obviously I, despite having used that for a long time, have never understood what it actually means. Can we search for GL clamp? Oops, it probably would just be called clamp, wouldn't it? In the GL docs, they leave off the GL. In the spec, they leave off the GL prefixes. So they're starting to talk about it here, but I'm looking really more for a so it looks like just regular clamp is actually gone now. So I guess the answer is clamp has been removed, and maybe that's why. I don't know. So this document won't tell us what the original clamp was defined to do. OpenGL 2.0 spec. All right. GL normally clamps such that the texture coordinates are limited to exactly the range 0 to 1. When a texture coordinate is clamped, it's either the texture sampling filter straddles the edge of the texture image, taking half its sample values and the other half from the texture border. It is sometimes desirable to clamp a texture without requiring a border and without using the constant border color. A new texture clamp algorithm, clamp to edge, clamps texture coordinates at all map levels since the texture's filter never samples a border texel. The color returned when clamping is derived only from text at the edge of the color. So I guess clamp actually was sampling the texture border. I didn't realize that at all. All right. You learn something new every day. Well, so that's fine. That just means we were setting that value wrong for everything. It just didn't matter because we always had an apron around the textures anyway. So I guess that's all fine. Yeah, all right. Well, there you go. Okay, so let's see here. I guess that's all. We are now drawing what we expect to draw, I think. And so I think everything's going through there except for pushRect now. So let's go ahead and get pushRect going through there. so that we can have everything going through that path, and then we can talk about what the next steps are, now that we have that digression into learning that GL clamp to edge is actually the proper thing to clamp. Okay, we've also got, so the store color there is now going through sRGB properly as well, which means the entity for our push cube color when we call sRGB linearize on this, that's turning one of our colors into sRGB. And then we're un-sRGBing it. So the question there is, are we properly preserving sRGB through this path or not? So when we do our push cube here, we do the store color. This is not going to do any sRGB conversions. So in the shader in OpenGL, when we're working with these, and those colors come in, you can see in here, right? If the shader, if sRGB is not supported, I guess it doesn't matter whether sRGB is supported or not. The colors that we pass down are no longer going to get sRGB converted by OpenGL anymore, which is actually a good thing. So what we want to do here is stop passing down sRGB. We don't want to pass anything down sRGB. We want to pass everything down in light linear space, which I thought we were actually doing, but let's verify that. So when we pass down here, we pass down a color. That color goes through unadulterated, right? Not modified in any way. And so when we do the multiplication by it here, again, none of that's sRGB. If we have to, when we actually go later to operate on that color, when we write it out, we have to simulate the sRGB reverse conversion. So that's what the square root is doing there. But I think everything else should be fine. We don't have to sRGB convert the incoming colors frag color like we do the texture because we're submitting it in sRGB ahead of time, right? So I want to look at what store color does though. So store color just does the pre-multiplication. That's the only thing it does. So that should be fine. And yeah, so inside world mode, when we do sRGB linearize for the push cube, I want to take a look at what happens here. sRGB linearize. That just squares everything. So that takes it from sRGB and puts it into takes sRGB and puts it into linear space, which is what we want to do. However, I'm just thinking about that. I feel like we're getting colors that are too bright, right? This is what we're passing down for sRGB linearize. And if you look at what we're getting here, that's very bright by comparison to what I would expect. And if I take a look at the values that are actually being passed down, let me look at them in ColorCop just to make sure. 31, 49, 32, right? Let me see if that's the right color. Well, no, that does look like the right color, doesn't it? I guess it just happens to be very bright. Yeah, all right. I take it back. So I guess we don't have any issue there, at least not that I can perceive at the moment. So our sRGB appears to be working roughly properly. And again, sRGB is in quotes because we're using squaring at this point because we don't have real sRGB conversion on this card because it can't do it, at least during the write phase. But we still got one more thing to do here, so let's go ahead and do that thing now that I've confirmed that there wasn't any funny business going on there. Let's remove bitmap and let's remove rectangle. And so now we're just down to textured quads and clip rect. That means we're going to have to get rid of push rect as well. So push rect is going to have to conform to the same procedure that everyone else is doing now, which is to say it's going to have to get the current quads render entry stuff and use that. So in here, when we do this push render element, actually what we're going to do is get current quads, right? And then when we do the get current quads, we're going to have to in here do something that push is on a rectangle that conforms to the specification that we were talking about before. Now, in order to do that, I'm just going to jump over to OpenGL, and I'm going to use, again, exactly the same process as before. We knew we were drawing a rectangle, right? This was the code for drawing the rectangle. It's going to come out. Here it is. So as you can see, all we were doing is just calling OpenGL rectangle with those parameters. So let's go ahead and go to OpenGL rectangle and grab that. And that is what we are actually trying to do, right? So we know we've got a couple different things here. We know we've got the min p and the max p. So let's go ahead and make a min p and a max p. And those were first what we called our entry p, and then our entry p plus our dim, right? And you can see what those ended up being up here. So the entry p was just the basis p, and the dim was just the scaled dim. Right? So really what we need to do here is just say, all right, we'll state the basis p, and then we'll do the min p plus the v4 scale dim, like so. And I think that creates exactly what we wanted to create. We have our pre-multiplied color here, again, like before. But really, we can just go ahead and say u32 color equals RGBA pack and get rid of all of these, because that's really all we needed, right? So now when we come through here and we want to start recording vertices, we want to do these push quads again. And so we're going to pass the group. The bitmap in this case is just going to be, since there's no textures on these rectangles, it's just going to be that white bitmap. And then we've got the P0UV0C1 situation. What we want to do here is just use exactly what we've got in this case. So this becomes V2. I guess these didn't have to be V4s, because I guess we're not using them that way, right? There we go. So really, we can just turn these into V4s. Again, there's no Z bias in this case. And again, we're just basically simulating, we're basically doing exactly what the OpenGL pipeline was doing for us with its fixed function before, which is taking a series of calls and turning them into just flat data that can be sent down to the card for use, right? So we're basically doing exactly that in preparation for doing exactly that. So then we just need to do this push quad with each of these. And in this case, since we have a lower triangle, upper triangle that was getting used by the rectangles here, we don't have to do that anymore. So we can just go ahead and use our final vertex as the final vertex of the quad and just use 4, right? So off we go. And now we just need to put the colors in there as well. So in addition to these, at each step, we're going to have to send down the color. Now, the color happens to be constant, so we're just passing the same color each time, so each of the vertices will have the same color. All right. Oops, don't still want that in there. So the min UV, max UV, in this case, I guess also is kind of irrelevant, but we'll put one in there anyway, just in case we someday want to have the rectangle have textures on it, I suppose. Oh, and I got to reverse the order of these. I was pushing them in the OpenGL order, which is not what I wanted. They need to be in our order where position comes first. Yeah. All right. And so now we still have the software renderer here, which we are not going to update right now, but we need to at least have it not cause us compile errors. So since we aren't supporting this anymore. Oh, wait, no, sorry, this is the OpenGL renderer. Yeah, we got to delete all this. All right. So now everything is going through that path, as you can hopefully see. And so that's all good, right? And now if I set a breakpoint in there, we should hopefully see more aggregation than we were seeing before, because now most things are going through that path. So hopefully most things should be able to get pushed into, like, they should be able to clump together. And so when we get one of these entries, we should see more quads in it than we were seeing before. So let's take a look at the entry quad count each time through. So here's a batch with 121 in it, 3,400, 121, 3,400. So we're basically just drawing in two batches now, as you can see, and that's great, right? Now, why is that great? Like, why did I bother? Why do I care about this? Well, first of all, one thing that you'll notice, there's a couple of reasons why this is an improvement, and we'll go through them in order here. So the first reason is we're sort of getting closer to a simpler format for the render layer, right? And that's pretty great, because if you can force everything through the same set of primitives and make those primitives very simple, it makes it a lot easier to optimize and make portable that render back-end layer, right? So now, even when we go back to do the software renderer, things get a lot easier because it's got less things to worry about, right? It only has to draw one type of primitive, and that's a textured quad, right? And it all comes through in one batch and says, hey, here's the whole set of textured quads for you to do. Just do them in order, right? So we simplify that back end by removing cases, right? The number of cases gets smaller and smaller, and that's just better and better for us, right? So that's all fantastic. Now, the other thing that's the important part about it, and the reason why I want to do it now, is because as we move away from the fixed function pipeline, which is what I wanted to do, I wanted to move us into just basically the core profile, which is the more modern way of using OpenGL, is we want to start talking in terms of batches of stuff we can hand over to the GPU without very much hand-holding from us. And previously what happened with those GL vertex calls, right, if you look at what's happening here where we've got these things like the old school way like this, where it's text chord vertex, text chord vertex, text chord vertex, these are calls into the driver every time. And if I go ahead and set a breakpoint OpenGL rectangle, which I don't know if it gets called anymore. So we'll probably have to force a call to it. Let me just go ahead and force a call there. Do, 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 do. So if I call OpenGL rectangle here, as you can see, I'm just going to force a call to it. It's a completely meaningless call, but that's fine. So here we are in OpenGL rectangle. Take a look at what happens if I go into the disassembly here, right? So what you can see is that all we're doing here is outputting a few vertices, right? All we're doing is outputting 6 vertices. When I come through here, I'm doing all the work to copy the vertices. You can see, I'm setting up the vertices here. That's what I would want to do, right? What I would want to do is just move this into some place where it's going to get used. But then I have to take the other step of calling into some completely other function in the driver, right? And you can see it's a double jump, so it has a jump through an indirection. Here is the code it has to go through. To do that, it's got another call, right? Here's another call we're inside, okay? I mean, there's just a tremendous amount of work. Look at all this work that's going on here, right? That was just for the color call. Just this one call, right? And so as you can imagine, that's just lumping this huge amount. The optimizer can't do anything with this because the call has to occur, right? It can't. This is a driver-specific call that's happening here potentially, right? You know, who knows what has to happen? AMD versus NVIDIA versus whatever. We have no idea. So the optimizer can't even reach in there and look at what that is or inline it. It can't really be inlined in any way. Because it doesn't even know what the code is doing. It's never seen it at compile time. So you end up in a really bad situation where there's a tremendous amount of work being done per vertex on the CPU side for no reason. Because fundamentally, all we want to do is just hand data over to the card, right? And so what I've done now is I've put us into a situation where we have a much cleaner way of working with this, where instead of that, we pretty much have everything, as you can see from here, we pretty much have everything in one big array, which if we wanted to now, if we had some way of just telling the graphics card, hey, graphics card, take this whole array from us, we would be all set, right? And that's exactly what we can do as we move away from the fixed function pipeline. So instead of having to make this call every time, where we go through here each time and say, okay, here's a vertex, 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 and doing a tremendous amount of work each time, calling into the driver 3 separate times for every vertex, right? Because we have to set the color, then the chord, then the vertex location. Instead of doing that tremendous amount of work, we can now drastically simplify that by just saying, here's all the vertices, and I'm just going to tell you what to do with those vertices in bulk, right? Now, if we were fully bindless, we could do this in bulk completely. So if we wanted to use like NVIDIA extensions, for example, we could actually do one call that would draw everything. We would basically say, I guess I shouldn't say one call. It's 3 calls. We would say, here's a pointer that says all the textures to use. That's our bitmap array. Here's the pointer that says all the vertices to use. And that's the vertex array. And then we just say, draw quads, right? Basically, is what we would do. It's not quite draw quads. It would be like draw tri-strips with a restart, but that's a separate thing. And it would just go through and draw them all. And that would be it, right? So at the limit, if you're programming a heavily programmable hardware and you're willing to use extensions, or you're on like a console or something, and so you know that you just have all the capabilities of the card at your fingertips, you don't have to worry about like Intel integrated graphics parts or these sorts of things which might not have the capabilities you need. You can actually take all of the load off. And this is what AZDO is, approaching zero driver overhead. The idea that you basically make almost no calls to the driver and you just give it huge sets of data and then it just interprets the data so that the driver and you don't have any need to communicate, and there's no overhead in translation. It's basically just shoveling things to the card. So once you put things in just some flat arrays that can be used, off you go. Now we can't get that good. And the reason that we can't get that good is because we're still using rectangular bitmaps. They're not packed in any particular way. So we need to tell OpenGL for every quad what the bitmap is that it's supposed to use, or in this case, since it's been sent down to textures, which texture handle to use. And setting the texture handle is something that requires a call. Again, if you don't have an extension. And like I said, if you are willing to use specific extensions for specific hardware, that's not true anymore. Because plenty of hardware does have the ability to switch textures per primitive, potentially, based on input data. Because depending on how the hardware is set up, if that is a generic operation, meaning when it goes to sample a texture, if it really just needs a location of the texture information, you can just supply that as data. Other cards, certainly older cards, but also I think still modern Intel cards, at least up to a certain point. I don't know about the very latest. They actually still required the concept of texture units and those units being bound. And so their hardware actually still had the limitation that when it was sampling from a texture, it had to be a texture unit, not a texture address. And at that point, it meant that every time you went through a new texture, you had to do that actual swap. So to the best of my knowledge, there is no way to get around that part yet everywhere. It'd be really nice if it was, because like I said, most high-end cards can just do this. And so you're kind of in this very bad lowest common denominator land where the only reason you have these APIs have all this ridiculous, stupid texture state associated with them is pretty much just because we still have legacy or less capable hardware that we have to support. Otherwise, we could have moved to something much better a long time ago where texture data was just part of the regular data that fed down, and you didn't have this sort of overwhelming state sort of management that is associated with switching a texture. Because again, a lot of things like texture atlases and stuff like that, they don't necessarily need to be used in a lot of cases if it isn't for the fact that you just have to worry about those texture state changes. And so it forces people to do stuff in certain cases that they really wouldn't need to do because the hardware doesn't really care as much as the API makes it seem like it does. But the reason that the APIs look that way is because of older or less capable hardware, not because the most fancy, modern NVIDIA part actually has those limitations, because it probably doesn't, is I guess the way I would say it. But all that is neither here nor there, because we still have to deal with those cards when we ship on the PC. So unfortunately, we're still in a situation where we will have to set the texture a lot of times. However, just because we have to set the texture a lot of times doesn't mean that we have to live with the rest of the sort of inefficient stuff that's going on. So we can do some stuff now to sort of help move towards something that's not going to have to at least send down vertices piecemeal, because we've done the work of that, and that is a nice simple change to make. Simple, in theory, not so simple because the OpenGL API is absolutely disgusting when it comes to this sort of stuff. Nobody really properly ever updated it, and it uses just the most heinous syntax, which is going to just be, it's just awful. But once we actually get through the torture of the actual set of calls we have to do, hopefully we don't get too many things along the way where I don't remember the exact magic ridiculousness that we specify. Hopefully eventually we'll be able to get it working, though, because once it works, it's fine either way, right? Anyway, there's There's a bunch of stuff in here. It's not client. It's, let's see. It's not array element. Let's see. GLDraw arrays. Let's start here. All right. And like I said, it's a question of me remembering all of these things. So basically what happens is, all right, so we have calls like this. GLDraw arrays, for example, you can see what it looks like. You give it a mode, and so you can see what the modes are here. Points, line strip, line loop, lines, adjacency, blah, blah, blah. So you pass basically what you're trying to draw. In our case, we want to draw quads, but of course we can't quite draw quads. So we're going to try to draw GL triangle strips, and we'll use a restart. I'll kind of talk about what that is in a second, but that's putting the cart a little bit before the horse in this case. Okay. So you call this GLDraw arrays, right? You've got the first, which says, hey, I guess there's some arrays somewhere, right? Which element did you want to start with? And then we've got count, which is like, okay, you're drawing arrays. What is the number that you want to do, right? And so you can see here, this is the indexed version. So in this case, I believe, or is this the indexed version? No, this might not be the indexed version. So this might be the regular version that's not indexed. So you can see what happens here is in the example code, and this is exactly what we're going to have to do. Here's the GLDraw arrays. It's going to draw a vertex count here. And what you can see is it first goes through a bunch of enable calls, and those enable calls say, here are the arrays that are going to be active at this point, right? Then we say, hey, in those arrays, here are pointers to where the data is going to come from, right? So it's basically saying, all right, in this array, I'm telling you that there's 2 packed floating point values. They're not normalized. This is what that, I believe, usually means. Here is the pointer to where they're at, and here's like the base of it. And we'll look at that call separately. Then we do GLDraw arrays, and then we disable all of those, right? So it's sort of a case of saying, hey, here's all the places to get the data that I'm going to use. Here's where they are in those arrays. Do it, draw them, and then end, right? Okay. Like I said, it's going to be real messy. So here we go in glvertex.trib pointer. This is the call that we need to be able to specify where the stuff is. This is the pointer to the data. And you can see you need these indices in here to tell you sort of where things are, right? It's basically saying which array you're talking about, because you can have multiple arrays bound at any time, right? So we're going to need these 2 calls. We're going to have to basically do what this says. And then we've got yet another thing that's a problem, because the other aspect we have of this is that this is what happens if you're using it with a fixed function pipeline. But we also have the problem of we're using a vertex shader. So in order to specify these things to the vertex shader, we also need a way of saying, hey, here's how you get the various values that the vertex shader is trying to read, right? So if we come back in here, you can see we've got this sort of vertex shader here. And you'll notice we've got a bunch of output variables, but we have no input variables, right? And that's kind of messed up. The reason for that is because we were trying to use the fixed function pipeline. So we had this like glvertex stuff going on here that is like a built-in variable that was getting passed down to us. Same is true of the text coordinates. We don't want to do that anymore. We want to convert away from the fixed function pipeline. So in addition, once we make that change, we're also going to need a way of saying how the vertex shader binds name-wise to the array elements that we're passing down, right? So we got to do all this crap. Again, it's complete busy work. The API is absolutely horrid. Like, it's just awful. But that's just the way it goes. One of the things you have to remember about OpenGL, one of the reasons it's been around so long, is they have a process for like accreting things together and moving the thing forward. They don't really have a process for stopping and going, wait, we've gone too far down this road, and it's all been bootstrapped off of the old way the API was set up. That doesn't make sense anymore. We need to wipe the slate clean and do a new thing that makes more sense with how people are using it now. that doesn't really exist. They tried to do it once or twice in its history. It doesn't really work super well. It's also designed by committee is rough when you get to stuff like this. It's a kind of thing where you end up just having just too many cooks spoiling the broth and that sort of stuff. So, you know, you got to take it for what it is, but it's an awful API at this point for doing this sort of stuff. There's just no two ways about it. But hopefully you can appreciate why the API is the way it is, and you know you can't really. It's hard to have something that lasts for this long, not get into a circumstance like this. I guess one thing you might say is it's surprising it's not worse than it is, right? So if you look at what's happening here, of the things we care about, we don't care about normals because we're not sending down any normals because we're not doing any directional lighting at this point. So we don't need those. So really what we're looking at here is we need to do enable vertex attrib array and vertex attrib pointer. That's really all we need to do in this case. So we need to set up these arrays, and then we need to specify that they're being used in a particular way. We don't really need to disable them so much, but we probably should just because we might want to mix other OpenGL calls in here at some point, I suppose. So we're looking at something that's going to look a little bit like this. But what we need to do here is say, okay, let's first start with getting our vertex specification down. Now, what you can see about vertex attrib pointer, and let's go ahead in here and see how this is. So we're going to ignore index for now because we're not going to look at that part of it. So let's take a look at the size, right? So the size here in this case is telling us how many elements we're specifying. So in our case, when we're specifying text chords, we're specifying 2. When we're specifying colors, we're actually specifying 4, not 3, because we have an alpha component. And in position, we're also specifying 4 because we have that extra z-bias component. So it's not what OpenGL, it's not what the people who are doing that example are expecting, which is just 3D positions. We've actually got 3D positions plus 1 piece of information. So then we've got a type parameter here that says what we're going to sending down. That's actually correct. We are specifying floating point texture coordinates, unsigned bytes for vertex for colors, and floats for vertex coordinates. Then we've got normalized, which is whether or not the thing should be normalized from the values set that it's in to 0 to 1 range. Obviously, for floating point values, that's not necessary, but for these unsigned bytes, it is necessary because we basically want them to take a value that's going to go from 0 to 55 and change it to one that's going 0 to 1. That's the normalization that it's referring to there. So we want to set that to true in that case. Stride, in our case, we don't have separated vertex arrays. We have one array of vertex data. Right? And so because we have one array of vertex data, what that means is we want to actually set this up so that all of our vertices are basically moving as you would expect, right? All of our arrays are pointing into the same array, but they're moving one full vertex at a time. So what this means is sort of the distance that it has to go is the size of our textured vertex primitive, right? Hopefully that makes some sense. So you can kind of see, all right, we're going to have these arrays, multiple arrays supposedly of the data coming in, but really we just have one array. So we need all the arrays to point into the same place. And every time they want to go to their next value, they're just going to go advance by the size of a whole vertex, right? And then similarly, when we come in here, we know that everything is effectively pointing to the same location, right? Everybody is going to be pointing into that commands vertex array. Right? So everyone is effectively looking at it like this. But each one of them is going to be offset by the address of whatever the member is that they particularly care about. Right? So what we want to do here is basically say vertex base or something like this. And we want to take this and cast it to a U8 so that we can do offsets on it. And then what we do is say vertex base plus, offset from, or offset of, do we have, what do we got here? Platform, let's see, offset of. So what we want to do here is say, hey, we've got the textured vertex. We want the offset of the one that corresponds to it. So we want, for our text chords, we want the offset of the UV inside it. And for the vertex space, we want the offset of the color. Sorry, for the color array, and for the position array, we want the offset of the position, right? And so just to underscore what's happening here, where is the pen? There is the pen. The pen is in my hand. So basically what we're going to do here is just say, okay, we've got a vertex array, and that vertex array is packed, right? So we have position, UV, color, position, UV, color, position, UV, color, position, UV, color, dot, 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 right? And OpenGL wants one array for each. So we have one array, but it wants 3. So all we're doing is saying, okay, well, if you want a position array, what we're going to do is point right here, and we're going to tell you the stride is this much, is one whole vertex. You want a UV array? Okay, well, we're going to point right here at the start of the UV, so off from the beginning of our array by however much the UVs are, and again, that same stride. So it's going to skip over the other 2 elements in the array, get to the next one, and grab that, right? And then finally, same thing, color points to here and skips over. So it's basically we're just setting up 3 array pointers to point into the same array. We're offsetting them slightly so that they point to the right starting member as if they were an array of just UVs or whatever. But then we set the stride to be much larger than a UV would be, so that every time it reads one UV, it will skip the interceding color and position values and get to the next actual UV value, right? So now we've told OpenGL basically how to get these out. And you know, you could imagine us setting this stuff up like so, with the vertex attrib pointers and all this other sorts of nonsense. But you can imagine we have some indices like this. Our problem at this point is still that we don't know what these indexes should actually be, right? And so in some sense, let me actually change it to something that we can talk about here. There we go. So that's a GLUint. So position array. Sorry, I guess I'll say P array, UV array, and C array. No, wait, yeah. All right. So, it looks like we still use a little bit here when we do the blend. We still use an OpenGL rectangle call. So until that's out of there, I guess technically what I'll have to do is move these down into the actual batch call, which is fine. Again, like I said, it's called so infrequently now because there's only 2 of these per frame that's okay. We can do as much setup as we want in there, and it's really not an issue. All right, so here we have all of our enable, disable stuff. We're going to have to get some of those functions. I don't think they were in OpenGL that early on. You can see that they're going to have to be things that we get. But we have some problems here, which is... What is the problem here? We still will have a problem here, which is we really just don't know what these values should be. And so that's the primary thing that we're going to have to deal with here. Is this color? Yeah. And so the primary thing that we need to know now from the documentation is where to get these. Now, one interesting thing about this is I suspect that if we want to try to stick with the fixed function pipeline again and just stick with it as long as we can at each stage so we can only do the change necessary to move one step closer. We could try to find out what the values are for the original OpenGL fixed function pipeline arrays. And so I don't actually know. I don't actually know if how possible that is. Well, yeah, I don't know. Let's go ahead and just assume that we won't be able to do that, or that it would take too long to do that. And we'll get, oops, I didn't mean that. We'll go along with, we'll just skip that part of the fixed function pipeline entirely and move forward. And maybe it takes longer to debug as a result, but oh well. Okay, so here we are with GL get attrib location. What is GL get attrib location? Well, GL get attrib location is the thing that I was talking about before. That's when we're looking at the this shader code. What we did before, right, is we had these things called uniforms, and we were saying, okay, these things called uniforms are the same for every invocation of the shader in a batch. That's why they're called uniform. They don't vary. And so when we're doing something like vertices and we're doing a bunch of vertices in a batch, then obviously something like the transform matrix that they're all using is going to be the same for many vertices in a row. Hence, it's a uniform. In order to set that, we use a thing called GL get uniform location, I think. We pass the program and the name of the uniform, and it goes into the shader and says, where is that name? What's the offset of that name that I need to set the right shader information for it or whatever? And that's what we used to talk about where the uniform was, right? And you remember we did that right here. You can see get uniform location, right? So now what we need to do is essentially do that same thing, but for inputs. So instead of relying on OpenGL to give us the vertex position and the vertex coordinate, and the UV coordinates, right, and the color, what we want to do is we want to specify those, right? So we want to say that we're going to get a vec4, that's the vert, position or whatever. We want to get a vec2, that's the vert UV, and we want to get a vec4, that's the color. Right? So we want these as inputs to our shader. And then instead of using something like GL vertex, we're going to just use like vert p. So we're no longer asking the fixed function pipeline for anything. We're going entirely our own programmable route, right? So now the fixed function pipeline is not referenced anywhere. The only thing that we do is the GL position is being used here because, again, that is a part that remains fixed function even in the most modern graphics cards you can possibly buy. Rasterization is just simply not programmable yet. So that is still fixed function. The blend unit and rasterization are still fixed function and probably will remain so for a while, I imagine. Maybe rasterization not, but blending, is rough. Anyway, there's a bunch of reasons why blending is kind of special. It's because of the multi-threaded synchronization necessary to make it all work fast. It's a bit dicey to make it programmable. Anyway, so if we go ahead and say, and I shouldn't say that programmable, make it, eventually it probably could be more programmable, but it would still have to be very fixed function. It would have to look like shaders where they're kind of like interleaved and understand what the things are. That doesn't matter. Irrelevant. Anyway, so what we want to do here is say, let's take these attribs and get their locations just like we did with the texture sampler ID, the transform ID, that sort of stuff. So what we want to do is say vert PID, get attrib location, OpenGL basic Z bias program, vert P. And then so we know we have vert UV and vert C. Vert color in this case. And once we get those, then we will be able to talk about those inputs specifically in the vertex shader and feed them, right? And so then when we do our enable vertex attrib array, that sort of stuff, I think I can't remember. Do we need to do the enable or not? I don't remember whether we need to do the enable or not, but I think we do, so I'm just going to. I'm sorry, this is, like I said, it's very weird the way this OpenGL stuff works. Oh, well, you know what? I can just assign them to the variables I've already got. Okay, and so now you can sort of see what's happening here. What we're doing is we're saying, all right, we know that this shader is expecting a bunch of inputs. We're going to get those inputs by asking the shader compiler essentially, where did you put them? Like, how did you assign them, right? And then we're telling OpenGL, here's the pointers we want you to grab for those, right? Okay. So now we just need to actually get these functions, right? You can see, well, I guess I have to define these as well. But we just need these functions that we're actually using here, and those functions have to exist. We also will have to do one other thing, which is that if you take a look at what's going on here, we're still drawing using the fixed function pipeline, which is not what we want to do. Again, instead of this, what we actually want to do here is we want to do one of those GLDrawArrays calls. And in order to do that, again, we need, so now that we specified our vertex space here, we need to basically say, well, all right, what vertex would we be drawing? And I guess this I can also sort of put inside here. That would be right there. So that is doing the vertices piecemeal. In this case, we just need to specify sort of an index. In fact, I guess what I could do is turn this into, let's do this. In fact, these could both be the same. Let me do one more transform on this first. Let's do an if1 here, and I'm going to if0 out these guys. Because I want both these paths to work. So go ahead and run that. Oh dear. Oh. Right. I can't run both paths because I changed the name in the shader. All right. So yeah, I can't test that. Never mind. I wanted to, but can't. That's all right. We can just do it blind. All right. So the other transformation I want to do out of here was just say, all right, so we're going to do quad index here. And so in order to do this quad index thing, what I actually wanted to say was, what if we just said, we know what the max vertex count is. Or rather, I should say, we know what the starting vertex is, because it's the vertex array offset, right? So what I was thinking is we could just say, hey, what if instead of quad index, we just did vert index here? We started at the vertex array offset, because that is exactly what that is. And then we ended at the vertex array offset plus 4 times the quad count. Right? Then we get rid of these two. And in here, where we want to get the bitmap, we're just accessing directly. Right? So it's just whatever the vertex index is shifted down by 2. And this one is whatever the vertex index is. So basically, those two just come out directly, and they don't have to be fussed with at all. Okay? So this stuff can now get put into this vert at doesn't need to be updated. So this stuff can now just go inside the quads version, so in case we ever want to try to put that case back together. And then we now have the draw arrays version can be much simpler. It can just say, GL quads, which again, I don't know if we can actually support properly. I don't know if it'll support our quad. So far it's been happy to do quads for us, so I assume we can, but I don't actually know. But then we've got the offset, which is just going to be that vert index. And then I think the primitive count is all we need. Oh, no, sorry. It is actually the number of indices. Yeah. So I'm pretty sure all we need to do here is then just say, when we do our GL draw arrays call, we know we're just submitting one quad at a time, and so we just call GL draw arrays with GL quads, right? And I think that's basically it. Now we just have to get those OpenGL calls. And also, I was a little overzealous there. The bitmap still needs to be accessed regardless. Here we are. And now we just need to get the OpenGL calls that we need for this, which is enable, disable, attrib pointer, and attrib location. So I will go ahead and get the core arb header out. And bump over to the Win32 side of things. There we go. And I'll just put these guys in there. So let's see. Get active uniform. None of this, that's not what we want. We want disable vertex attrib array. Get attrib location. And attrib pointer. There it is. All right. So I do also think maybe, based on how many of these we have, I feel like I could have saved myself probably a lot of time at the very least by not using the complete complete lower casification, for lack of a better term. Right, because it's probably just easier to do something like that. Just saves a lot of typing. And similarly, when you've got stuff like this, you could automate it a little bit more. So I might sort of switch over to that. Right, because let's say we did this. something like this. And then we just have the name of it. We know what the format of that would be. It's just going to be global variable type underscore the name, and then the pointer name, like so. That seems like a lot better, right? So if we were to do something like this, then what we can do is just say OGL global function. So we might as well have OpenGL global like that. And you could even go a little bit more ridiculous with this, right? You could use a pound include. You could use an include file that had these listed and use some macro tricks to make it even fancier if we wanted to. I'm not inclined to go that far, but you know, we could. So if we have something like this, right, then what we can do is the same thing could be true down here. So we could do a pound define like 32 get OpenGL function name. And when we've got one of these, we would just say like, okay, the name equals type name get proc address stringize name, and off you go. And so you can just do win32 open get OpenGL function and just put the names in. So I probably should have done that to begin with. I just always thought like, oh, we're just doing a couple of these. I won't think too hard about it. But you know, eventually we ended up deciding to use the full OpenGL pipeline stuff, and so at that point it becomes a bunch of typing if you don't actually take a second to save yourself some of it. So you know, maybe we could convert those over at some point into it just to be a little bit more consistent. Anyway, let's go ahead and start debugging this. Well, that's just lovely. I think everyone can agree that that looks fantastic. Amusingly, it sort of works, which that's not. Usually I expect when I do a change like that more of like it's a black screen or something, right? But in this case, it's not. So anyway, let's see what we've got here. We probably just have a few mistakes in terms of how we're setting up our specification. So let's go ahead and take a look. I'm going to flip this around so I can read the part I actually care about at the top instead of at the bottom. There we go. So we have our vertex index here, and we're starting with index 0, and we're going to whatever the 4 times the quad count number of vertices. Oh, that's supposed to be going up by 4s. Hey, look, that was a lot better than I thought. We're not getting any texture coordinates or textures, but we're getting close. All right, so let's see what else we've got here. Maybe our UV array is messed up or something like this. We are pointing to the correct offset, it looks like. In this case, we've got the UV array is 2 floats. It's not normalized. It's the right size. So that all looks pretty good. When we're binding the texture here, we're presumably binding the right texture. It's the vertex index shifted down by 2, which I think is exactly what we'd expect it to be, because that's where it would have to be. I don't see any way that could not be right, unless I'm missing something. So let me take a quick look to make sure we are enabling it to, right? Yeah, let's make a quick check here. We've got vert UVID is getting vert UVID out of the basic ZBias program. Let's see what's going on there. That's the problem. The ID was on the end, which it shouldn't have been. Okay. So now we're in a good place here. Now we're actually using pretty much none of the fixed function pipeline along that path, which is nice. And we're drawing everything that we want to draw. So now we're drawing using the GL arrays call, and that's a better, again, stepping stone to getting us completely off of the fixed function pipeline. So if you take a look at what's happening now in here, again, the number of calls to OpenGL has been drastically reduced, even though we're still not at the point where we're hands-free or anything. It's much closer. So as you can see now, we make just a few calls here. We make about 9 calls, like one here, 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 and then here, 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 right? So make those 9 calls to set things up, and we make 3 calls to shut down, 4 calls to shut down, which we could probably save some of those if we wanted to amortize, but yeah. And then remember, like our numbers in here were 121 and then 3,000. So these calls are very minimal. They hardly ever happen. They only happen twice per frame, so we don't even really care about those. So all we care about is really inside this loop. And so we went from calling OpenGL 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 times per quad to calling it twice per quad. Once with the texture and once for the instruction to render one quad, right? And so what you can see is we've gotten down to a really good place for us by comparison, but like I said, we would like to do much better than this, right? Like what we would like to do is be able to just set those 2 arrays, all the vertices and all, because we know that they're all quads, all the vertices in that one buffer, all the texture pointers in another, we'd like to just say go. But like I said, I don't think we can really do that in this case. And the reason for that is just because there's no way to use like multiple bitmap pointers in a way that works across all cards. But now that we've done that, we can also just sort of get rid of this stuff here entirely. This is no longer necessary. And this becomes a pretty nice little function, right? And like I said, it would just be nice if we could get rid of this loop, but we can't really get rid of that loop without a bunch of without using some kind of extended OpenGL. All right, let's go to a brief Q&A now. Oops. There we go. Kim Jorgensen, would it be better to expose an OpenGL get proc address method in the platform layer and do the lookups in the handmade OpenGL layer? So it depends on what you mean by better. Unfortunately, I guess what I would say is, unfortunately, the term better in this case it depends on what you're aiming to do. If you're trying to be more cross-platform, then no, it's not better. And the reason for that is some platforms already have a bunch of these things built in and don't allow you to do a get proc address call to get them, right? And so on those platforms, it would all break. However, you could use a macro, and that might be okay, because then that macro would just do it like it equal, like this function pointer equals itself kind of a thing. So I would say, yeah, probably not exposing the get proc address call, but you could expose a macro and have that be included, and then it would probably be better because then the platform layers don't have to duplicate it for ones that do have to do the get proc address, if that makes sense. Valbus, we will use, will we use vertex buffer objects and index buffer objects? In that case, do you prefer using GL buffer data to send the data into the buffer or using map buffer, unmap buffer to send the data? So the answer to that question is it depends. At this point, no, there's no point in us using vertex buffer objects or index buffer objects. First of all, index buffer objects we definitely don't need and would never need, as far as I know, because our vertex data is unique per quad. So we save nothing by using indices. If we had shared vertex data ever, then an index buffer makes a lot of sense, obviously. So index buffers, not something we need. Vertex buffers, on the other hand, would be something we needed if we weren't still having to make one call per quad. Since we're at the point right now where we have to make one call per quad, which is not good at all, right? You do not want to do that. Going to something like vertex buffer objects in order to save some additional performance time in terms of how things are specified down to the card just doesn't make a whole lot of sense, because we're already way too slow because of this stuff here, probably, to care about something like when the copy happens of the vertex data. But if we wanted to do a path at some point that actually took advantage of bindless textures, for example, then absolutely vertex buffers would be the way to go, because we'd just put everything in the vertex buffer and then have the dispatch call go, and we'd never have really any driver stuff happening at all, which would be great. To answer your question about map buffer, unmap buffer versus GL buffer data, the answer there is it depends entirely on your circumstance. You need to test the two and find out which one's faster. In some circumstances, map unmap buffer should be faster because it can avoid an additional copy. In other cases, map unmap buffer will not be as fast because the driver has to synchronize at that point to give you memory that it can use. And so it depends a lot on how you're doing it. Now, keep in mind that there are new APIs in AZDO that allow you to map a buffer and leave the buffer mapped. And that is probably going to be the fastest thing eventually, but the extent to which drivers support it and it works well, I don't know yet. I do use it on our code at Molly Rocket right now, but I haven't shipped that platform layer out to anyone but myself, so I don't really know if it's something you can trust on. Robbie, will you use ForCoder in full window mode for ed-f in the future? I don't think I knew that there was a full window mode. But it sounds like something I would like. Is this, you know what? I'm on 4.0.10 here, though. Is that something that got added? Is there a command line reference? I don't know if there is. I may have to update to the latest version of ForCoder. Hold that thought. By moving the construction of the vertex array to the render group, we kind of missed the opportunity of writing the quads directly into driver-owned memory. Is that statement correct? If so, is that a problem? No, that statement is not correct. That is, in fact, what you're getting at there is exactly why I structured it the way that I did. So what you'll notice here is I was very careful when we did that part of the code in the platform layer to enable that kind of optimization if one were so inclined. I don't know that we will be so inclined. But here you can see the game render commands. And as you can see, the textured vertex array is a pointer in the game render commands. All we do in render group is write into this address, right? So you can see that, all we care about inside the render actual code that's in the platform independent side is that we have that pointer and we're writing into that pointer, okay? That pointer comes from the Win32 side, right? So in here, we've got this code at startup creates that buffer that's being used. So if we want to, in the future, write directly into a hardware-backed buffer, all we have to do is make this code right here call OpenGL to get us the buffer. That's it. All the rest of our render code is already set up to do exactly what you're talking about, which is write directly in to the code in question, right? Kim Jorgensen, couldn't OpenGL get proc address just return the method directly on some platforms using string lookup? Yeah, it could, but then now you haven't saved yourself any typing, right? Now you have to type in all of the strings somehow and all of their mappings, which is the function, which is exactly what you were trying to avoid, right? So, you know, the only reason to do what you're talking about is to save yourself typing. So you have to make sure you do it in a way that doesn't create the typing somewhere else. And I think doing a macro does do that, right? So you could just say that, well, okay, the platform layer, before it includes OpenGL.cpp, has to pound define like function lookup as a macro, and then the OpenGL layer just does that, and maybe that macro just returns the same name it's passed directly, so it basically just like function pointer equals function pointer, or it expands it to wiggle get proc address parentheses open quote blah blah blah, right? So we could absolutely do that, but I think that's the way to do it. Because if you did it any other way, I think you'd end up in a situation where some platforms just have to duplicate all the typing that you were trying to get rid of in the first place. Jesse Meyer, why not build one massive vertex buffer and just draw that once? That's exactly what we are doing. We just build one massive vertex buffer. But the problem is we have no way in, without being specific, as far as I know anyway, without being specific to certain graphics cards, that we can actually dispatch the entire draw in one call. The reason for that is every quad has a different texture. So we need to set a different texture per quad, right? So what you can do if you really care about this, and like I said, we would have to first find that we actually had performance concerns that we needed to address before we would do this. But what you can do, this is where texture atlases or texture arrays or things like that come into play, where you start to do things like packing things into a single texture so that you don't have to change textures inside primitive dispatch. And again, it's stupid because a lot of cards don't need that. A lot of cards don't need you to specify textures outside of the batch. They can specify textures inside the batch because it's just a piece of data that's used during the texture lookup, which can just as easily come in as all the rest of the data. But because that's just not true on all hardware, you end up in these circumstances where the programmer has to do a lot of extra work to get that, such as packing things into an atlas or a texture array. Because atlases and texture arrays are not different textures, right? They're one texture with a way of indexing into them. In one case, it's the UVs in the case of the atlas. In the other case, it's an index in case of the texture array, which allow you to basically essentially specify a different texture per primitive by using something that the cards can do for indexing, that all cards can do. Jesse Meyer, I see, thanks. Any chance we can see a render call stack from Nsight or RenderDoc just to see what the driver has to work through? I don't know if we can actually get that working on this card. I need to replace the graphics card in this machine. It's very old. That's not what I want. I don't know if we can, because it probably just won't work, but we can try. Let's see. If it works, awesome, but I just don't know if it will. Because this graphics card is really old, and I just don't know if these sorts of things can be finicky. If it works, that's going to be awesome. But I just don't know, because it's great for debugging too, which we've been fortunate, we've been careful, and we haven't run into anything that was really hard to debug. But, how do I get to the downloads? There we go. But that's just because, well, and we're not doing anything really complicated in the shaders or anything, right? So all right, so I usually use Insight. I pretty much never have used RenderDoc at all. But let's see here. If I open it up, we'll see if it does anything. Just thinking about it. All right, let's see here. Executable path is W handmade. Oh wait, W build 132 handmade. The working directory is handmade data. We don't need a command line arguments. So let's see what happens if we tell it to go. Only OpenGL 3.2 plus context are supported. That might be a problem since we don't create one of those, but we could. So if we came in here and changed it to an OpenGL 3.2 context, we probably could. So let's try that. So maybe this is working. Don't know. Not seeing a lot here. So yeah, I don't know if just to conclude that it's probably not going to happen or what. Let's see. Oh, you pressed F12 to capture. Okay. Like I said, I've never used this before, so I only ever use Insight. Oh, it crashed my program. Where did it crash the program? Okay. Not sure what's going on here, folks. There we go. So we crash inside RenderDoc. RenderDoc is jumping to null. So it's trying to call. You can see we get pretty deep down here, drilling for oil. And then we hit the 0. And so this saucy gentleman right here dispatched to 0, 0, 0. So I don't know what that implies exactly. That could be because, again, if this card doesn't support certain calls that it needs or something. But there you go. So the answer is no. I guess you can't see a driver call stack, but yeah. Does the debug UI still work? If so, how does one activate it? We haven't done that yet, no. It's pretty much will just work, but we have to go do the orthographic transforms stuff. But after that, it will work. Jim O, have you set a version target for the pipeline? Will you go full embedded systems bananas OpenGL ES? Well, no, we probably won't really support anything other than a platform you would ship a game on, but that would include, you know, OpenGL on Android or something probably. All right, I gotta close it down because I gotta get going here. It's getting late. All right. I am pretty pleased with how that all worked out, though. I mean, we're basically running through shaders now and our own data set up. The game looks good to me. I think it really just now needs artwork to be dropped in there. So we're getting close. Next week, I feel like I'm going to be away for the weekend, so we won't do anything next week. But the week after that, when I come back, we should be able to sort of clean up the last remaining stuff that we might want to clean up in certain terms of like eliminating anything fixed function, and probably we could then switch over to just the core profile and have the core profile be entirely all we use. And then we're pretty fully modernized. Like I said, the only step I don't know that I'm going to take is trying to texture atlas our assets or anything. And the reason for that is just because I don't know, I think it's some diminishing returns there. I don't know that we have the kind of performance profile that's going to really care about the texture swaps. We may just have to do one thing, which is add one other primitive type, which is a bunch of things that are rendered with the same texture, and use that for particles when we get particles in there. I think that might be all we really need to do. So I think that's probably the approach I will take. I won't try to go the Atlas route. But we could also play around a little with some NVIDIA extensions and just for fun do a version that does all the things in one draw batch by using bindless textures, because that would be just kind of fun. And it's eminently possible. So yeah, that's about it. I'm going to wrap it up now. Thanks so much for joining me for another episode of Handmade Hero. It's been a pleasure coding with you as always. If you would like to follow along at home, you can always pre-order the game on handmadehero.org. It comes with all the source code so you can play around with it. There's also a forum site you can go to if you'd like to support the video series, a Patreon page you can go to. I'm sorry, I switched those. A forum site you can go to if you want to ask questions. A Patreon page you can go to if you want to support the video series. A schedule bot you can use to know when we're going to be live. And an episode guide you can go to if you want to catch up on old episodes. That's about it for this week. I will be off next week. I'm not going to be around. So I expect to not have a Handmade Hero stream next weekend, but we'll be back the weekend after that to close out our OpenGL modernization pass. Because I think we've basically done all the stuff I wanted to do. And so we've kind of got that stuff nicely cleaned up. That's about it. Thanks for joining me. Have fun programming next weekend without me, but I'll see you guys the weekend after. Take it easy, everyone.